about okay. So yeah, many of us, I think, are used to thinking about atoms and perhaps ions as useful tools in the lab and perhaps for quantum information. And so today I thought it'd be good to give some important information on how you take this idea of using an atom or say an ion as a quantum computation platform and like actually turning it into something in the lab where you can walk in and say, hey, I want to do some sort of quantum mechanics with my ion that might help me, one day realize an actual quantum computer. Okay, and so to start that process, I wanted to talk to people about spectroscopic notation and selection rules. So generally, spectroscopic notation is a way to write down angular momentum quantum numbers of an electron state. So it's a way to specify the state of an electron in an atom. And the base formulation looks like this. So you have this term here, this N with the superscript 2s plus 1, and another term here, L with the subscript J. N effectively sets the average distance of an electron from the nucleus of an atom. This S here specifies the electron's intrinsic angular momentum. The L here specifies the electron's orbital angular momentum. And then this J tells you about the electron's total angular momentum. Now, when you want to start thinking about how you might turn an atom or an ion into a qubit, you need to think about what energy levels are allowed in the atom and which transitions between these energy levels. Let me rephrase that. You need to think about which energy levels exist in the atom and which transitions between these energy levels are allowed. And you can do that by thinking about these things called transition selection rules. And so we think about these in terms of these matrix elements that look something like this. So you think about some initial state psi connected to some final state psi through some operator. This is how you can start to think about determining your qubit. Now, there's a number of different kinds of transitions. I want to point out dipole transitions. These are sort of the most usual transitions, I would say, where you think about how your initial state and your final state are connected via this position operator, or if you want to write this in position space and actually use wave functions, this is an overlap integral between this initial state, this final state with the position R, okay? And what you find from looking at these overlap integrals, you can definitely check whether or not they're zero. And you find that for a dipole transition, the matrix element is zero, unless delta J, the change in the total angular momentum of the electron, is 0 or plus or minus 1, with the exception that J equals 0 to another energy level where J is also 0 is forbidden. But you also have a quadrupole transition, where again, you're thinking about which overlap integrals are 0 or not. Effectively, this overlap integral looks like an integral over the position squared. And you find that quadrupole transitions allow delta J equal plus or minus 2. Okay, there are some exceptions there, but this sort of is the important thing that I want to highlight as a possibility. Now, it turns out that atoms have something called hyperfine structure. You should not only think about the intrinsic angular momentum or the combined or the total angular momentum of the electron in the atom, but also how the magnetic field associated with the motion of the electron interacts with the intrinsic angular momentum of the nucleus of the atom. Together, these two things, I plus J, this is the nuclear spin, you get this quantity that the community calls F. And so you also have selection rules for F based off of this, this expression for F, I plus J. And so altogether, you have that, you have transitions between different energy levels labeled by F, where delta F for the transition can be 0 or plus or minus 1 for dipole transitions, or if you're thinking about quadrupole transitions, also plus or minus 2. Okay, and so here I've included energy level diagram from one of the Campbell group's papers, where you can see this sort of base labeling for these electron states, this 6.2p1/2, the 6.2s1/2. This is what I described here. And you see that because of hyperfine structure, these energy levels split into these f equals 0, f equals 1 levels, or f equals 1 and 2 levels, or f equals 0 and 1. Okay. And so when you're looking at these sort of energy level structures, you want to think about which pair is sufficiently isolated from some other energy levels, such that with some nice tools, say a nice microwave generator or a nice laser, you can make an effectively two-level system. And so in this picture, there's sort of 3 qubit candidates, and there are other practical considerations that you should think about when determining what might be the qubit candidate for you. Now, this sort of energy level diagram is not only useful for thinking about which states you can use to form a qubit, but also to do some practical things in the lab to make this a useful platform, namely laser cooling. And so I'll ask that people sort of keep this picture in mind of energy levels and the differences between them, which we can address using lasers, and how we can use this to cool down atoms. But first, we should trap the atoms or the ions in order to move towards being able to do interesting quantum mechanics with them. How might you do that? Well, a common way that people do this is with a Paul trap, specifically a linear Paul trap like the one I've drawn here, which refers to the trapping of a charged particle via alternating electric fields. And so in this image, I have these 2 ground electrodes, the silver colored ones. I have these reddish colored electrodes that have a very large oscillating voltage applied to them. And so you can use this sort of scheme to trap ions here, little blue circles in the middle. You can trap them along this rail. And so if you look at the potential generated at some time snapshot, say t equals 0, you might have this, what you have is a potential that looks like this saddle point here. So in this direction, you have some positive curvature. In this direction, you have some negative curvature. Now, I said that this is an oscillating electric field. So if you look at the potential half a cycle away, you see that this potential has effectively rotated. And so if you imagine averaging this potential, this rotating saddle point over this period, then what you effectively have is this parabolic bowl where the motion of your ions are defined by the curvature in this bowl. Okay. Now, at this point, you have your ions trapped, but they are very hot. The ions could have energy something like 1 electron volt, which if you convert that to an effective temperature, this is thousands of Kelvin. And so this is very hot, and we want to be able to cool down the trapped particles so that their motion don't sort of make fuzzy the different energy levels that I showed. This is important if you want to do some precision addressing of different energy levels, say for making a qubit. Now, the first part of reducing the energy of these trapped ions, these trapped atoms, would be through Doppler cooling. Okay, so imagine that I take my barium atom that I started talking about in the last slide, and I shine 2 counter-propagating lasers on it. So I have a laser coming from this way, I have a laser coming from this way. If I'm careful about what the frequency of the lasers are relative to some transitions, one gap between the energy levels in the barium that I showed you on the previous slide, then I can apply forces to the atom that are the result of Doppler shifting the light frequency to make it look like the light is resonant with some transition in the atom. And so the sort of canonical picture I think people tend to think about when they think about the Doppler effect is, an ambulance moving away from you, right? This is a situation where you have yourself, the detector, and you have the emitter, the ambulance, with some relative velocity, and you notice that the pitch of the ambulance siren appears to change with the relative velocity between you. We can use this effect in atoms where you slightly detune your frequency. You make the frequency of your laser less than what you need to make a transition between electron states. And if the atom is moving towards the light, in the atom's frame of reference, the light looks resonant, so you can absorb a photon that gives you a momentum kick in the opposite direction of the velocity. And if you do this, if you average this process over many cycles where the photons that are absorbed are emitted through spontaneous emission, you have a process that extracts energy away from your atom. So you can cool it down. And so there's a nice graph here which shows the force as a function of the velocity. And there's this gray region, which is the capture range, where should your atom start with some velocity in here, you have this condition, the force is proportional to minus velocity, you can cool them. Now you can take this cooling a step further and use a process called sideband cooling to really get your atoms cold. Sideband cooling is a procedure that cools the intract motion of your particles to their quantum ground state, which people typically refer to as in the average in the occupation of your harmonic oscillator being less than 1. Right, so the energy of your ion in its harmonic trap is the quantity n plus 1/2 times h bar omega. And so typically when that n is less than 1, people say it's in the quantum ground state. You can do this similarly to how I just described, where you have some transition, some electronic transition you want to address. You have your laser be slightly detuned to lower frequency. And that gap between your laser frequency and the transition you want to excite should be the frequency of the motion of your ion in the trap, right? So the moving atom will scatter light, so you're at your laser frequency plus its motional frequency and minus its motional frequency. And so if you make the scattered light, that is your laser frequency plus the motional frequency resonant with the transition, you can siphon energy out of your atom. Now, the first time this was done was with the Mercury Ion, I believe in Wineland's group back in the 80s. And they measure these sidebands associated with scattering, basically absorbing and creating and absorbing phonons or mechanical motion from your ion. And they measure an average occupation of 0.05, which corresponds to something like 100 microkelvin temperature, which also means that about 95% of the time their ions are in the ground state. Okay. Sort of another nice way to visualize this is this picture of harmonic oscillators, where this harmonic oscillator is associated with the atom being in its ground internal state, its ground electronic state. Okay? And it has these quantized energy levels. This is what we know about the harmonic oscillator. I can change the atom's internal state from the ground to excited state by sending in some photon with h bar omega naught of energy. But if I send some light in that is some laser light that is this frequency omega naught minus the motional frequency omega motion, then the scattering process that I mentioned will take me up to this excited state, and then spontaneous emission will take me back down here. So now I'm back in my ground electronic state, and I have one less quantum of vibrational energy. And I can repeat this process and take my atom into its quantum ground state. Okay, so now I'm going to talk about state preparation to actually do the qubit operations. And at this point, I have a very cold, maybe 100 microkelvin ion. It's in a trap, but that entire process has put the atoms, kind of spread the atoms across this manifold here, across these different f equals 1 states and this f equals 0 states, where the f equals 1 and f equals 0 here. In this picture, this defines my qubit states. Okay, so you need to go through a process to prepare your state for its initialization before you do whatever qubit operations you want. And you can do that through optical pumping. So this is a diagram for ytterbium, and you can drive this transition here, say from f equals 1 up to this state. And then you use the selection rules that tell you that this state will decay into this state. And so you can drive this transition between f equals 1 here and f equals 1 here over and over and over and populate this state here. Okay, eventually you do this, you find that your steady state situation leaves your ion state very, very mostly this. So in your block state picture, This is the state that you start with. This is your prepared state. Now, we know that the general state is described by a superposition of the ground and excited states, the 0 and 1, that have some time-dependent coefficients, and they're normalized in this way. And so if I put this into the Schrodinger equation, I find that the amplitudes, say C1, has a sine square dependence on time. And so depending on how I apply microwave pulses, I can create some general state psi. Okay, but there is a potential error here in state preparation. So there is some, even though you use some laser to drive transitions from this state to this state, there's some non-zero probability that you drive a transition from here to here. And that's not good, because if you do that, then you can have atoms then fall from this state back to this state. And that's not where you want them. You're trying to put them here, right? So this is a possible way to have an error introduced in how you prepare your state. How do you go about state readout? Okay, well, generally, when you're thinking these ion systems, when you're reading out a state, you're doing some sort of optical pumping, like I showed before, switching between these two states, and you're observing the presence or absence of fluorescence. So you're collecting photons and you're measuring how many that you get. And you integrate this fluorescence to say which state your atoms are in. And so in this picture, again, this is my qubit, 0, 1. You can drive this transition from f equals 1 here to f equals 0 here, measure the fluorescence. Right? That tells you about part of the population of your state. You can apply a microwave pulse and rotate your qubit between here, and then do this process again and compare the results. Right? You can read out your state in this way. Now, some difficulties with this is you might be trying to read out your state by only driving this transition from here to here, but you might accidentally drive a transition from this state, f equals 1 to f equals 1, which then decays into f equals 0. And so this ion that was initially part of your bright state here, it becomes a dark state ion, and it no longer scatters photons, and you need ions to be scattering photons in order to measure, in order to read out your states. This is a bad thing. Not only do you need these ions to be able to scatter enough, you also need to be able to collect enough of those photons to actually confirm your state. Okay, and so when you think about all these things together, the state preparation and state readout, it's useful to talk about a total figure of merit fidelity associated with state preparation and measurement, SPAM fidelity. And this is important because the bounds that you can put on your ability to read out your state depends on how well you put your atoms into the state you think you did, and vice versa. So it's nice to sort of to combine this figure of merit in that way. And a natural question is there a way around these difficulties or errors that I mentioned? And so one thing that the Campbell group likes to use is some sort of shelving techniques. And I suspect that Wes will have quite a bit to say about this, so I won't say too much. But generally, what you do is you move your atoms or your ions to some state manifold that's isolated from your readout light. So in the previous slide, I showed how off-resonant, unintentional transitions between states can put your ion into the wrong state, which stops you from being able to read out the state you tried to initialize. Okay, and so in this work where they're studying ytterbium atoms, they use some cycling transition between this F state here and this one here. This is a delta F equals 2. So this is then using quadrupole transitions. And this transition has some dipole transition to some other state that's really long-lived. But also this transition is very narrow. And so they're able to minimize the chances of putting the ion into states they don't want to by utilizing this narrow transition. And basically scattering photons from changing the atom state from here to here, you're scattering photons. The ion can go to this long-lived state here, or it can go back down to this state here, at which point it will just be scattered again. So they can move their ion states into this manifold here. and really make use of the fact of not accidentally putting the states into ones that stop them from being able to scatter photons and do measurement. And so just like in the previous case, you can do some sort of pi pulse that allows you to rotate your qubit between these states here. And you can do this measurement again and compare the fluorescence you get.
Charles, I am so sorry for interrupting. It's just super nice. We're a little bit running over. I just wanted to let you know.
Yeah, this is my last thing. Sorry.
Okay, great. Thanks.
And so you can create a sort of histogram that looks like this, where you count the number of occurrences versus the number of collected photons, where you can use some discriminator and say to the right, this is associated with your excited state, to the left with your ground state, and use this to extract your fidelity. And so with this, I think this is a nice background to help understand the concepts that Wes will be talking about in his presentation.
Perfect. Actually, Charles, let me interrupt really quickly. So actually take a quick look at your chat, which might have something helpful. But let me also share my screen for just 1 second, because I forgot an important announcement that I want to make just before Charles introduces Wes. Actually, next week, despite the fact that it's spring break, you will not be without a colloquium. There is the UCLA CQCS seminar series. And actually next Thursday at 10 a.m. will be Alon Ospru-Guzik from the University of Toronto. So you can go to the CQSE.UCLA website to find the details for that event. Or I think Eric or Wes will try to put some information into the chat for everyone so that you can access that directly. All right, perfect. Turning it back to you, Charles. Sorry.
Okay, no problem. All right, so yes, on to Wes's talk, but let me first give a quick introduction. A number of years after receiving a highly prestigious certificate for excellent participation in science in Mrs. Borgman's first grade class, Wes Campbell went on to Harvard, where he worked on molecule cooling and trapping. After receiving his PhD in 2008, he began a postdoc at the Joint Quantum Institute, where he helped to develop the use of mode-locked lasers for trapped ion quantum information processing. At UCLA, Wes's group is in the Department of Physics and Astronomy, where he's been focusing on applications of mode-locked lasers for slowing and cooling difficult species, as well as development of new tools for trapped ion quantum information processing. So with that, please take it over, Wes.
Thank you so much, Charles. The fact that it went over a little bit is actually great, because you didn't actually, you freed up some time for me by going over so much material, essentially. So thank you. Okay, so today we have a talk, but it is also a holiday, right? And so in the grand tradition of Americans celebrating March 17th with a dignified and accurate celebration of Irish heritage, we're going to have a little game here for those of you who have a coffee or a festive beverage. Every time you see something that reminds you of the Emerald Isle, we'll have a little toast, okay? So you can drink. So we'll try to keep it light here, and just remember that there's a difference between taking your work seriously and taking yourself seriously. So the starting point for sort of where I'm going to jump off from what Charles talked about is a little bit like the starting point for our institute, which is that this whole endeavor has come to life in an era when we've had some recent results demonstrating what we call quantum supremacy, or the ability of quantum processors to calculate things that are beyond our classical computing capabilities. I think we're going to be hearing talks that start with a slide a lot like this for a long time, okay? This is basically what we're all thinking about. We have this wonderful result right now, and the question is, where do we go next? How can we get more out of this? How can we turn this into something that is closer to what we ultimately want, based on this result? And one way to look at it is to start thinking about fidelities. And the fidelities in this work, there were many, many gates involved here. The circuit is sampling the output of a pseudo-random quantum circuit. It took about 1,000 single qubit gates, each of which has a fidelity of 3 nines, about 400 2-qubit gates at 2 nines, and there were 53 qubits, and you had to do state preparation and measurement, and the measurement fidelity anyway was about 0.96. And somewhat coincidentally, when you go through the math there, each of these contributions ends up being about a factor of 0.1. Okay, so the overall fidelity, you know, that you get just due to the single qubit fidelity is about 0.1, so on and so forth. And so you get about 10 to the minus 3 at the end. This is the fidelity of the actual computation. So the probability of this device providing you an output that is not corrupted by an error was actually quite low. Okay, which is, you know, not something that the authors tried to hide in any way or anything like that. I'm not accusing them of doing anything wrong. This is the era that we're in. We are in this NISQ era, this kind of noisy intermediate quantum system, quantum scale or quantum system era. And so we've got 99.8% classical noise coming out of this. And the remaining 0.2% is, unless I am mistaken, sampling from a distribution. So when this processor does execute its algorithm with no errors, it is not producing a state that is an eigenstate of the measurement. And as a result, the measurement itself brings in, you know, what we call quantum projection noise. Okay, so we've got mostly classical noise, and then we have quantum fluctuations on the remainder of the output. And so this might be, you know, one of the things that we can look at as an avenue for improvement here in the future. Okay, so one of the things I like about this seminar series is how deliberate we're being about starting discussions. Okay, and so I have my intentionally provocative topics for discussion time. And this will be my first version of this. And the first one, you know, I want to ask, what have we learned and what can we learn? And we've had some discussions about this before, even. You know, it's just kind of something that I think we could still be scratching our heads about. I think there's no question that we have learned a lot of engineering in doing experiments like this. You know, there is a lot of little science. There are a lot of little science projects that go into a big project like that. And so certainly there's some science in there. But, you know, if I want to think about the output itself, you know, we can ask what we've learned from that. Another thing is, you know, when we think about that output, unless I'm mistaken, it is generally producing strings that are not reproducible or testable for correctness. And these are things that when we teach our students, our young students, about science and, you know, what is the difference between science and religion and things like that, you know, we look for reproducibility and whether something is testable, at least in principle, you know, for correctness. And, you know, in practice, testable for correctness, it's even better. And so this is, you know, maybe one of the things that we'll be thinking about how to move forward on. Is it dope? Yeah, for sure, right? I mean, this was really cool, okay? And let's not forget that the public has gained interest in what we're doing, perhaps for many of us for the first time in our careers. They have heard of quantum computing. It is being funded at an unprecedented level, and occasionally we're going to need to deliver on this. And the Google team delivered. Okay, so they did one of these things that we said we were going to do, you know, within the framework of calling this a quantum supremacy demonstration. And then last, of course, is the output useful? And I'm going to say probably not yet. Very low signal to noise ratio, as I was discussing. And we need to find a way to sort the results that were produced without an error from those that are simply noise, classical noise from the errors, okay? So we want to do useful things, and we still have limited qubits. So a framework for talking about this is to think of a low bit game, okay? We're in a game, we don't have very many bits, we don't have very many qubits, so here's what it is. It's a quantum quest. So if any of you played Sierra games back in the days when they had those, this is the type of thing that I'm depicting here. And what we have is a showy object of little use or value, if I'm going to be super, you know, strict about this, okay? What we have, I think a lot of us are excited about, but we're not really, you know, cracking codes at these things yet, or whatever, you know, whatever it is that you might be interested in. And so we have a gym crack. Like the device that I make in my lab is a gym crack. It is one of these, okay? And many of us have these in our groups. And we want to get from there to something with computational speed that is amazing, right? We want the ludicrous speed. And so, you know, there is a pathway there, but of course we're going to run into things that we didn't anticipate. So maybe since it's St. Patrick's Day, I'll say cheers to everyone. We've got an adversary. Our leprechaun here is going to get in the way of what we're doing. Okay, we're trying to steal his pot of gold, and he shamrocks errors. Okay, so I don't like this guy either, but the fact of the matter is that something is going to be getting in our way, causing errors, decoherence, all this stuff. And so we're gonna pretend like we got a little adversary here in this leprechaun. So what can we do about errors? One option is what I'll call the plutonium-powered car solution here. Okay, if you imagine the possibility of a car powered by plutonium, that is awesome. Okay, all right. So our option that is like that is to correct errors with a bunch of extra qubits and 2-qubit gates. And this is a brilliant idea, absolutely. And just the existence of this idea is really important. It could solve everything that we do. This could be the way that we operate in the long term, you know, whether you're talking about the quantum computing or the plutonium powered car, right? You know, we've got no fossil fuels, you know, we can produce a calculation to arbitrary precision. But unfortunately, we're not there yet because that solution uses resources that we don't have in abundance right now. Okay, the most scarce resources we have are arguably qubits at this point, or at least high quality qubits that are connected in the right way. And that, you know, puts some constraints on how useful error correction schemes that utilize a bunch of extra qubits and 2-qubit gates can be in this regime. Okay, you know, further compounding our difficulties, we can't just skip to the point where those are going to become solutions for us, because I think that it is anticipated that this will be the solution in the long term, but we ain't got no time machine. Okay, so I'm going to propose the non-plutonium power car option here. I'm going to call it the green quantum computing. I don't have a solution for you. I'm just really going to spend the whole talk talking about the problem here. But, you know, somehow using abundant and renewable resources, we want to be able to identify, reduce, and correct errors. Okay, or errors. All right. So cheers, everyone. This is our trinity, our shamrock of dealing with errors. And we have to do this in a way that uses the minimal number of extra qubits and the minimal number of 2-qubit gates. That's kind of the two things that are the hardest that, you know, to use right now. Those are the resources that we care about the most. So trapped ions have a niche in the quantum computing community associated mostly with their fidelity. This is the thing that trapped ions are particularly good at when you compare them to other platforms. I think every platform has its strengths. Certainly, if you're willing to extend your definition of what the goal is to things that are sort of analog simulators and stuff like that, all the platforms, you know, bring something. But trapped ions have wonderful fidelity. And in fact, it's so high here that I don't like sitting there counting the nines. Like I might like the number, but I don't like counting nines. So I'm going to switch this to errors in decibels. Okay, so this is 10 log base 10 of the error. And the single qubit errors are kind of 6 nines of fidelity, minus 60 dB or so for the best trapped ion demonstrations. 2-qubit gates are at about the 10 to the minus 3 level, right? About minus 30 decibels for that error. And the coherence times for single qubits are now exceeding 1 hour in these systems. Now, this is not something that necessarily every single piece has been demonstrated all at the same, you know, same time in the same device with a bunch of other qubits there. We're not there yet, but as existence proofs, this is sort of the lay of the land. Now, the way the processor works, and Charles gave a great introduction to linear Paul traps. If we have a bunch of these ions in our Paul trap, we're going to use lasers to interact with them, and they can couple between the motion of the ions and the qubit states. We'll identify a couple of states in these things as qubits that we'll talk about in a second. And that is how we can perform quantum logic. They can exchange phonons with one another as this crystal has normal modes of motion. It's a quantized degree of freedom. Further, I think it's generally accepted that a solution for scaling the system up is not going to be a single crystal that has 1,000 ions in it, but rather we're probably talking about modular systems where we have crystals of ions and locations and we shuttle them around, okay? And this is called the quantum CCD architecture. But the idea here is that by micro-patterning electrodes, we can make a more complicated Paul trap than the simple linear trap, and we can actually control the positions of these things and move them around to do our logic. Okay, so inside our ions here, just as Charles was saying, we have some choices on how we make a qubit, and one of the choices is a Zeeman qubit. Okay, this might be the first thing you would think of. If we have a doublet S1/2 ground state, which I'm going to assume here, that we can just identify the different projections of the spin on the quantization axis and call those your qubit. And that's certainly a possibility. It has a couple of drawbacks, not the least of which is that the splitting is not that big in a sort of reasonable sized laboratory field. This is also extremely magnetically sensitive, sort of, kind of by design, okay? But magnetic fields are ubiquitous, so that causes some problems. Another choice is to do what people call an optical qubit or an optical frequency qubit. Here we identify some metastable electronic state, and we choose levels within those manifolds to define our qubit. And the qubit splitting there, instead of being 100 megahertz, is more like 100 terahertz. And so this is actually an optical laser that you would use to address this instead of radio frequency waves. And if you want to have a long coherence time, like a coherence time of 1 hour in a system like this, then you require a laser line width that is 1/1 hour. Which is one of the technological things that people work on in this field. And the third flavor is a hyperfine qubit. This is what Charles talked about. The idea here is that there's nuclear spin. I know that we have kind of a mixed audience here for this talk, including computer scientists and stuff like that. I don't want to scare you away by talking about nuclear spin. I just want to point out that it's useful, okay? The fact that the electron and the nucleus interact leads to a splitting in the atom. And that hyperfine splitting can be a technologically convenient scale. Something like 10 gigahertz is very nice for us. I will just say that. It is large enough that we don't have to worry about a bunch of noise sources, but it is still a low enough frequency that we can use kind of synthesizers and things like that. It's actually right about where you would want to be. And then I'll call type 3A would be a specific version of the hyperfine qubit where we have a spin 1/2 nucleus. So it's a spin 1/2 electron, a spin 1/2 nucleus. And that gives us just enough hyperfine splitting. We have this just enough hyperfine splitting to have our 10 gigahertz qubit, but nothing more. And while I am going to try to argue that having a lot of states is a useful thing, it is also true that if you want to have a bunch of states in your atom, it can be inconvenient if they're all bunched up right around the same energy as the states you want to differentiate from them, your qubit states. So having lots of states is good as long as they're kind of elsewhere. So state preparation, Charles gave a great intro to this. I'm going to show you the same thing again, just because I think seeing it twice is probably worth it. The F=1 to F=1 transition here is what we can use to actually, we call this optical pumping. We're going to dissipatively push all the population into the spin up state, okay? And that's just based on the selection rules that Charles was talking about. And the theoretical kind of limit that you get with this based on the atoms where people use this and what that structure is like is about 6 nines of fidelity, okay? About -60 dB. For theoretical state prep fidelity, something like that. And then what we'll call standard state detection here involves illuminating it with light on the F=1 to F=0 transition. And so this light can take population up to that P state only if the qubit is found and spin down. And it can spontaneously emit. It will have to go back to the F=1 state because of selection rules. And this is kind of rinse and repeat. You can keep doing this a few times. And by a few times, I mean about 10 to the 4. So just based on the fact that there is some off-resonant excitation probability that Charles mentioned, that's about what you get out of this. You can do it about 10 to the 4 times before you've mixed everything up. And that sounds like a pretty good deal because, boy, 10 to the 4 photon clicks is really easy to distinguish from 0. which is what you would get if you were in spin up. But the problem is that they're emitted in a random direction. And these things are not likely to hit your detector. As a matter of fact, you have to work quite hard to make them hit the detector. And so it's more typical to get something like 10 clicks out of it when you make all the efficiencies and add them all up. And by working really hard at things, you can get the spam fidelity to a level of about 3 nines. So minus 30 dB for that infidelity using this technique. Okay, so let's talk about that in the context of an algorithm where we're doing quantum error correction. Okay, our quantum error correction scheme involves identifying some of the atoms as being data qubits and some of them are ancilla qubits. And we're going to do 2 qubit gates to prepare a syndrome. We're going to measure an ancilla qubit, and based on that result, we can use that classical information to correct the data qubits from an error, and then we'll reset it. Okay, and we got to repeat this a bunch. This is during the algorithm. Okay, we're doing this essentially repeatedly as we are, say, running a quantum algorithm. And if you think about doing this in an ion crystal, a problem arises, which is that when you're doing the measurement of the ancilla, a photon can hit another ion that's emitted by the ancilla ion. Okay, it turns into something else. In this case, it's a shamrock. But the point is that it can corrupt the quantum information on a neighboring qubit. And the likelihood of this is actually kind of annoyingly high because the scale associated with an atomic absorption cross-section is about the same order of magnitude as the scale associated with the ion spacing here. They're both kind of order a wavelength. And so this possibility means that there's going to be crosstalk even if your laser beam is perfect, which is a challenging thing to achieve. So even if the laser beam doesn't hit any other ion except that ancilla ion, if the neighboring ions can absorb that light that it is spontaneously emitting, you will end up corrupting that data. Okay, so one of the approaches here to get around that is to shuttle them around like that quantum CCD architecture. And this is something that the Trapped Ion Photonic Integration Working Group here at the CIQC is working on. And this is a group that consists, I would say, in terms of the meetings, it's largely Ming, Bubakar, Eric, who looks somewhat untrustworthy here today, and Hartmut. And Bubakar and Ming are the experts on the photonics side, and Eric, Hartmut, and I kind of come from the trapped ion side. And what we're coming up with is a platform where we can shuttle ions around and address them with optics that are on board the actual trap chip and multiplexed. So using these switches that Ming makes. And so the species that we're probably looking at for this are calcium and barium predominantly. I'll talk about that in just a moment, but we're looking for the construction of these devices as well as the characterization of their performance with regard to something called anomalous heating, which I think Hartmut may talk about at some point in a later seminar. The material choice here, the process identified silicon nitride as something that can work for some of these species. And right now the progress, really being spearheaded at Berkeley with Hartmut's group is already producing trial devices for combining as well as splitting waveguides to actually distribute light to the ions. So the last piece of atom anatomy that I want to go through, at least in terms of the gross structure here, is to review once again, Charles gave a great intro to this, the electron shelving technique, because that's really important. And for this, we need this D5 state, this low-lying metastable state. And the idea is we take one of the qubit states and we dissipatively move its population into the D5 state. Then we can cycle photons from the ground to the P state on the using the other one. Okay, and that might happen on the P1 state. I should correct that slide there for the cycling part. Okay, and so now that we know what we want, we're ready to choose an ion. So we have the whole periodic table available to us, and the assumption that I've made that we have a double S 1/2 ground state was based essentially on lack of imagination would be one interpretation, but this makes things easy. They're laser coolable, they have strong transitions. and some qubit states, essentially. And if we are going to constrain ourselves to those species, which I might argue is not probably the most adventurous thing to do, but might, be a reasonable place to start, the periodic table gets reduced to this. Okay, so this is my periodic table of the ions that are used for quantum information processing, essentially. All of these are doublet S1 half ground states. And since it's my periodic table, I get to name them. So we have the alkaline column, we have terbium is on an island all by itself. And then this last one is what I like to call the ultraviolets, because they require light that is deep in the UV. So the parameter space that I'm showing you here is one way of looking at how you choose an ion, and the y-axis is a proxy for how difficult are the lasers. So higher in the vertical direction is easier lasers, lower is harder lasers, and all that zinc family are at the very bottom, because those are really challenging wavelengths. The x-axis here is the lifetime of that D state. If we want to do electron shelving or have an optical frequency qubit, basically if we want to have another stable state available to us to use for things, we want a long-lived D state. And that leaves really radium, strontium, calcium, and barium. However, none of those have a spin 1/2 nucleus. And so by going through this process, what we've learned is that we have nothing left, all right? And this little guy is feeling very smug about it because he is our adversary, but I will say that we're not done yet. So don't declare victory, Mr. Leprechaun, because who says we need to have a naturally occurring spin 1/2 isotope? And David Huckle says we certainly don't. And so David really deserves a lot of credit. He came to us about 5 years ago and said, we should do this thing. We should make barium-133 trapped ion quantum computer because the half-life of this, it's radioactive, it's a synthetic isotope, but it's got a half-life of 11 years. Okay, so this is not what you would call T1 limited limiting. Okay, this is, if we end up being limited in our coherence time because of the radioactive decay of the nucleus, I'll be pretty happy because that means our coherence time is really, really long, basically. So it's not that bad. And in terms of dealing with the radioactivity, let's keep in mind that we're talking about machines that have of order 50 qubits. That means 50 atoms. So the total quantity of radioactive material I have to put in my vacuum chamber does not need to be Avogadro's number, okay? It can be an edible quantity of radioactive barium, okay? It really does not need to be detectable, I would claim, okay? And so this project is a collaboration, I think many of you know, with Eric Hudson. We work very closely with one another on lots of things, and this is one of our projects that we collaborate on. And the features of barium that give it, kind of nice aspects here are essentially bolstered by the spin 1/2 nucleus of the barium-133. So it gives us that high fidelity, fast, very easy state preparation step that Charles talked about. It is also the prettiest atom. I will say that. If you have an atom that is prettier than this, I will challenge you to an atomic beauty contest, because this thing, it is like a rainbow, all right? At the end of the rainbow, I think we all know what we expect to find. Cheers. All right. And these are really the colors that we have. And since it's a trapped ion, for those of you who are kind of experts in the experimental atomic physics, you might look at some of these wavelengths and say, yes, they're very pretty, but the technology for creating that light is nasty. But this is a trapped ion, and we know precisely where the trapped ions are in the trap, and we can focus a laser beam down to a tiny, tiny spot size to hit them. So when we only need a microwatt of 585 nanometer light, that is significantly easier to produce than 50 milliwatts or something. And so these are all diode-based systems. They're all very, very straightforward. Another way this is the prettiest atom is that it just works. This is the qubit, or we're doing Rabi flopping, just a magnetic dipole transition here. We're driving with microwaves on the hyperfine qubit in the ground state, and it just goes on forever and ever. Okay, this is the decoherence is not discernible in this plot. All right, we have to do a lot more Rabi flops before we get to that point. So this is just gorgeous. It just works right out of the box. The actual implementation of electron shelving in this system is that we drive from the f=1 state up to this p3 state here. And there is a 614 nanometer photon that gets spontaneously emitted at some point after doing that a few times that puts that lower state into the d5 manifold, okay? And once it's up there, we can then turn around and look for fluorescence. And this is an example of one of those histograms that Charles was showing. So this is what it is for barium-133. What I'm showing you is a histogram of the number of clicks that we get on the detector. So it's a histogram because we repeat this many, many times. And the yellow histogram shows you the result when we try to prepare one of the two qubit states, the so-called bright state, which is the f=0 state. And the red histogram shows you how many clicks we get if we try to prepare the other state, the f=1 state here, which is the so-called dark state. And by setting a discriminator, just saying if it is fewer than 16 clicks, it must have been dark. If it's greater than or equal to 16 clicks, it must have been bright. We end up with a spam infidelity of about -35 dB. And so this is better, this is an improvement on kind of what the community had available to it before this thing. And the reason this has been so good is simply the atomic structure. It's just what are the splittings, what are the kind of line widths and things like that. Okay, so I have more intentionally provocative topics for discussion time. I was provided with some questions by the postdoc organizing committee, and this was one of the questions. So they asked me if I could assign a team to work on something else, what would it be? I mean, I have a bunch of answers I'm going to put up here, but I'm also going to use this maybe as a little bit of a drum break. So if folks have questions, I will say I'm happy to take questions right now because I'm about to kind of change gears and start talking about ytterbium here. So I'll put these up and ask if folks have questions about the other things, because the stuff on this slide, that probably we should save for after the talk, because this is, stuff I'm telling other people to do, so it can be a little crazy. No question. Let's see here. No questions? All right, good. All right. Remember this slide. Remember what you want to ask about if you have something on here you want to ask about. Okay. So next we can think about the far more popular ion compared to barium, which was not popular certainly before barium-133 kind of got introduced and is still less popular than ytterbium. Ytterbium is really ytterbium and calcium are probably the two most popular ions that get used there. I know Hartmut's group up at Berkeley uses calcium largely. We use ytterbium largely. In my group, the reason that this was not on the list was twofold. One of them is it's a little bit in the UV. So it's just above the line there that I call the direct diode line. And what that means is it's just barely easy to make the laser cool it. It is also, however, the d5 lifetime is really, really short in barium, in ytterbium. And it's only 7 milliseconds. So in barium, it lives for about 30 seconds. Okay, so when we shelve population up into that d5 state in barium-133, we will see it decay eventually, but it's generally not a limiting process for us. But in ytterbium, this would be. And part of what happens here that is unique about ytterbium is not just that it decays back to the S state, but it has an additional state. There's a new state we got to deal with in ytterbium, and it is this F state, doublet F7 halves. So the first excited state in ytterbium is an F state, and that thing is the decay from the F state to the S state. Okay, that violates all the rules that Charles told you about decays. Okay, it is not an electric dipole, a magnetic dipole, an electric quadrupole, or even a magnetic quadrupole transition. It is, in fact, an electric octupole transition. So the lifetime of that F state is actually on the order of years. So it's effectively stable. It's basically another stable state. So people have not really taken the idea of shelving very seriously in ytterbium because of this decay. But my student Tony, around the time when barium was starting to look like it was getting quite useful with the electron shelving fidelities, he started thinking about ytterbium, and he said, you know what, we should do this. You can actually shelve one of the qubit states in ytterbium by driving an electric quadrupole transition in a dissipative manner. So this is what you might call an open channel that is also narrow, which is a strange combination of words, but there it is. By using this 411 nanometer light, we can go from S to D, which is an E2 transition, and it will cycle essentially, and we can optically pump into the F state. And so looking at the ultimate fidelity that you can achieve with this, the barium infidelity here is, somewhere around, minus 35 dB. And the ytterbium infidelity, the predicted by theory, is shown in the green there. And so if you're willing to shelve for a long time, then you can, in principle, get this fidelity to be quite good. Now, shelving for a long time is not going to be great in a quantum error correction scheme. Okay, if you're trying to make measurements during your algorithm and do something based on the result of those measurements, you don't want to wait 200 milliseconds to do that. But you also don't need the spam fidelity to be very high for that, because you can generally just repeat your syndrome measurement and take the majority, right? You do it 3 times, and if you get the same answer twice, then you say that's the real answer, right? So even if the fidelity is not great, it's actually not that big of a deal for quantum error correction. But at the end of the algorithm, at the end of your big long computation, thinking about the Google quantum supremacy experiment here, you want to know the right answer. You worked really hard to get the right answer. And if you have a register of n qubits and the readout fidelity is f, the probability that you get the right answer is f to the n. And is exponential in the number of qubits. And so you really need that fidelity to be quite good. And I'll also point out our standard state prep error, it turned out, in ytterbium was not the minus 60 dB that I told you about. It was about minus 41. This we found experimentally, and we think it's because the diode that we're using, the diode laser, has like some what we call amplified spontaneous emission, or amplified spontaneous emission that is actually creating some light that is off resonant on that thing. So we had to come up with a new scheme that I can tell you about if you're interested in. But the point is that we did not actually even get that minus 60 dB, and probably everyone thinks they get that, but no one has checked. So it's amazing what you find when you get to the 10 to the minus 4 level. So the barium, just remind you, this is what we found in barium. The histograms here are chosen, the illumination time is chosen here so that those histograms basically just barely touch, okay? Because the amount of time you can spend illuminating this thing is limited eventually, by that D state lifetime. In ytterbium, the F state lifetime is forever, so you can drive a truck between these two histograms here. But we're still in the process of, trying to do our analysis of these data. So far, it looks like it is at least as good as the barium-133 result. So a related but different technique, but it seems to work pretty well. It's limited by different physics, essentially. We are not limited by our ability to distinguish the metastable state from the ground state. So beware of people who are making big claims about fidelity based on that distinction. That distinction is easy. Qubit spam is much, much harder, actually doing state prep and measurement. Okay. So looking back at this, we've got our ytterbium experiment has learned from the barium experiment. The barium experiment is also continuing to learn. And what are we learning? Well, certainly our qubit states, we have to have these in our ions. The P states are obviously useful. Okay, we use these for fluorescence detection, state preparation. We have learned that the D states are also really useful. And the take-home message here is that more states are good. More states is good. Okay, having more states is good. And this is probably not something that I would have said 10 years ago. 10 years ago, I would have said you want the simplest possible atomic structure so that you don't have to have repumps and everything gets easy. But the more states you have, as long as they are well behaved, the more you can do with your atom. All right, we are now getting very good at working with these atoms, and so we can get more creative with the structure. And so one example of that is in the ytterbium F state. Remember, this thing lives for years. And because the ytterbium-171 has a half integer nuclear spin, that F state has two states that are magnetically insensitive. It's a qubit, all right? It's a qubit that lives much longer than any algorithm we're going to do, all right? So this is also effectively stable. You know, we don't worry about the barium nucleus decaying, and we shouldn't worry about the ytterbium F state decaying, at least not in ytterbium-171. So we can use this thing as a qubit. And now we have kind of 4 different qubits in this atom, all right? You can sort of pair up whatever you want here on these m = 0 states. And at the same value of the magnetic field, namely B = 0, they are all insensitive to magnetic field fluctuations to first order. So that we have simultaneous clock states. We've got 4 of them available. The way that we operate this thing is by dissipative, we do heralded state preparation. That's what I'm trying to say here. So the idea is that if we can get some of our population up into that F state, we can preferentially optically pump some of them down to the S state, which is bright. And then we can look for it with our 370 nanometer light. And if it's dark, we know it wasn't in that state. And by eliminating everything except the state that we're interested in, we can herald the preparation of a pure eigenstate in this thing. And so far, infidelity, it looks pretty good on this. It's not competitive yet with the barium-133 or ytterbium ground state numbers, but we did kind of just start this business. So that, yeah, we see it. All right, he's very proud of himself. Okay, but we think we know how to get around some of these issues. So we're still working on it. It's not clear exactly what the limit is going to be on the spin fidelity of this thing. Okay, this issue, if you recall, crosstalk, is now absent from this process, if you think about it, okay? Remember, the light that you have to emit during the detection process I've shown above is 1 photon at 289 nanometers, and then 10 to the 4 photons at 370 nanometers. And so as long as that single photon well, in fact, that one you don't even care about. Neither of those affects the F state. So if all of the ions start off in that F7½ state, and the beam for 760 nanometer light is technically perfect, right? If it doesn't hit any of the other ions, then none of the spontaneously emitted photons here can actually corrupt the data on the neighboring ions. So this obviates the need for shuttling for the purpose of, isolating the spontaneous emission of ions from one another. There are other reasons that one might want to do that. So I've got about 5 minutes left. So it works great. The qubit, we can do Rabi flopping. There are lots of choices we have available going forward using the metastable qubit to couple to motion. In fact, we have a whole manifold of metastable states available that are metastable above the metastable state. So all of these states are at least electric quadrupole decays, if not higher order decays, as their first allowed process. And it is, once again, a rainbow. All right, we've got our pot of gold at the bottom of the rainbow. And this just illustrates further, I think, the utility of working with things that are more complex. We can now choose, and the multiplicity of these states is huge. We have a ton of states available to us in principle. So we can now make choices based not just on what the atom hands us, but also which lasers are convenient. So we'll be exploring some of these, trying to look for what's going to work in the future. One of the capabilities we have here is to do a projective null measurement or quantum non-demolition measurement. So if we prepare the X eigenstate in our in our metastable qubit, what we can do is randomly depump either the spin up or spin down states, and then conditioned upon not having a bright state ion, we can continue to Rabi flop. And if we do that, we get noise, right? Because we didn't keep track of which state we projected into. But if we keep track of it, we can separate those two and we get nice, high contrast Rabi flopping. So this is a projective null measurement. It's a capability that, kind of I think if theorists imagine that all ions can do this, but they can't. This is kind of new. It's very hard to do this with ground state ions. It typically involves multiple species and coupling to motion, all kinds of stuff. But in the metastable qubit, it's quite easy. So if we think about our sorting the wheat from the chaff in the NISQ regime, okay, how do we know when we've had an error? How do we know which results to trust if we're in a regime where most of the results are not trustworthy? We can think about amplitude errors as being one of the sources of that noise. And that's the one that I think about the most because amplitudes are difficult to control compared to frequencies. And so we have a scheme for this. And the idea is that if we start in the metastable qubit state, we're going to identify two more metastable states called the auxiliary manifold. I call them A1 and A2 down here. And let's say our target operation is an X gate, a single qubit gate here. We are trying to take alpha up plus beta down to beta up plus alpha down. If our amplitude errors are common mode to multiple frequencies, we can transfer population into the auxiliary manifold. Always has some finite error, right? I'm an experimentalist, it's always finite. But after outcoupling and confirming that the ion is dark, we now have done a perfect transfer of population. We can then repeat this process with slightly different frequencies essentially that are chosen based upon what gate we want to drive. It doesn't have to be an X gate, it can be anything. We then clean out the auxiliary manifold. Again, if we've done things well, we're likely to get a dark state qubit. And as soon as we do, we can verify that we did this gate without common mode amplitude errors. And so it's a way of sorting the wheat from the chaff. It's just one particular type of error that can happen. But at the end of the day, we have a certificate that our gate was not corrupted by that particular type of error. And I think generalizations on this would be really useful in this NISQ era. So, we can think about our errors as being digital or analog. Usually there's, there is a measurement process at the end. So, there is no, I would say, formal distinction between these two, but the way I think about it as analog. Okay, when I think about errors, I think about them as analog because they're typically classical in origin. There are also quantum errors, but this is the stuff that, kind of the approach that I'm advocating for here. So when we talk about quantum error correction, it is frequently, it goes like this. We consider the errors to be a transition. We have leprechaun hat operates on psi, turns it into psi error, right? If, by the way, cheers. If we can engineer things so that psi error lives in a state space that is orthogonal to the space we want to use for computation, and that's kind of half the battle, is that one thing, then what we can do is check the error subspace. And that's how we can learn whether we had an error here. So it kind of comes down to doing that and then being very clever in how we look for, how we measure that and how we use that information. So our quantum quest here, this is I think my last or second to last slide. What we want to do is make that error subspace with the fewest number of atoms. Okay, that's the goal. I've argued here that atomic qubits have tons of states inside them. And so I think more thinking about this could be a big help. Things along the lines of the sort of, GKP codes or the molecular codes that John Preskel's been talking about. If we start thinking about atoms as having so many states that they are continuous variables, that might be an avenue, but somehow or another, using more states inside a single atom instead of using more atoms is probably a fruitful avenue for pushing us forward. So the folks who did the work here, the Ytterbium 171 team, Tony recently graduated, is now at Honeywell, and Conrad led, I think, a lot of that work as part of his thesis. The Barium 133 team, Dave Huckle deserves a lot of credit for kind of pushing us into doing this. He has his own group now at AFRL. And Justin Christensen graduated from that project, but the folks here are the ones who really do all the work. So I think with that I can close up and offer to answer any questions.
Thanks, Wes, for a really, really awesome talk. So if you wouldn't mind not sharing for now, so we can see you, we can take some questions from the audience. Oh, actually, there's one in the chat. Maybe I'll go ahead and read it with the background. Okay, so this is from Dan Samper-Kern. When you plot fidelity of detection with your histograms, you're only keeping track of the total number of counts. There's more information in the light emitted by the ion, timing, pixel index on the camera, polarization, etc. Can we use that information to boost the measurement fidelity? Is the answer different in the case of detecting one ion versus detecting one ion among very many?
Yes. But I can go, I can elaborate more. Absolutely. So, you know, one of the pieces of information that is useful is the arrival time of the photons, because if that metastable state can decay, then you might expect that if that process happened, you would get very few clicks for a long period of time, and then all of a sudden you get a bunch of clicks. And Eric Hudson and Jens Paulberg, who both may be here in the audience, have been working on machine learning algorithms for identifying those processes. The location of the clicks spatially on, say, a camera or something like that is also, of course, very important for reducing measurement crosstalk. So the readout crosstalk, if you have a dark ion next to a bright ion, you might get bleed over between those two. And that is related also to how many clicks you can get. So in the ytterbium system, since we can sit there all day, I mean, the metastable state doesn't decay, remember, ever, essentially. We can average down that process, that spatial information, to get that out. But in ions where you can't do that, that crosstalk is important. There are also more kind of machine learning things that people think about on that stuff. So absolutely, there's information in that light. I haven't thought about polarization. Usually we have a pretty large solid angle collection system for these things, which can tend to kind of mangle polarizations up a little bit. I haven't thought too much about that, but that's an interesting possibility.
Do we have any more questions from the audience?
May I ask something very naive? Hi, Wes. Great talk. Let me just ask something. So the kind of fidelities you spoke about and the capabilities you spoke about seem to be quite a bit beyond the kind of things one hears from IonQ, for example. So is that because you know, do the things that you talk about scale, or is it just that you know, by the time you scale them up, then you lose a lot of them, or is it just that they haven't gotten there yet, or should they be deploying what you are saying?
So you know, of course, I think they should be deploying, you know, what I invented. But you know, that's kind of a nonsense statement. Yes, it gets harder when you have more ions, when you are scaling up. I don't think that there can be any question about that. So the heroic numbers I was showing really early in the talk are, I mean, that you're doing that and only that, you know, and it's a single ion, and the world is completely perfect. And so, you know, the types of things that get involved when you have multiple ions, the collision cross-section for a large chain of ions with a background gas molecule is n times larger than a single ion. You know, that's one thing to think about. You also have crosstalk, which is absent for a single ion. The motional spectrum is more complicated, the heating, you know, things like this. So, so it's absolutely the difference between a scaled system and an isolated system. And that's an important difference. I mean, you raise a very good point, which is that, you know, while it's nice to be able to demonstrate something with really high fidelity, it is still a gimcrack, right? I mean, it is still not the useful device. And it's very important to take the numbers from people who are using large systems with lots of capabilities very seriously as well. So you can't just say they're not good at it, because it's not true. It's really, you know, their numbers are also very impressive, would be one way to think about it.
So can I ask a small follow-up question? So let's say you do a 2-qubit gate, and it's in, you know, and you have many other ions as well in your trap. So now, should I be thinking about the gate fidelity as, well, so these 2 qubits are going to be, you know, there's a chance that there's going to be an error there, but at least as far as the rest of the qubits in the trap go, they are not subject to any error while this 2-qubit gate was being done. So the reported numbers are just for these 2 qubits and everything else is left alone, or what do those numbers mean?
I don't know the answer to this. I can tell you that there is potential crosstalk of the laser beams literally hitting other ions during the process. And that's something that people think about and work on. I don't actually know if that is a limiting infidelity at this point. If it isn't, then the infidelity during the gate is most likely due to residual spin motion entanglement. And if they are performing gates and then cooling again using ancillary, use kind of refrigerator ions, then I think it is fair to assign it kind of just to those two ions and move on with your life. But if they're doing it and there's residual spin motion entanglement, and then other ions start interacting their spins with that motion, you know, that can actually lead to correlations.
Mm-hmm. So sorry to you know, just to keep following up, but my understanding of an ion trap computer is that you do one gate at a time, but you think of the spins are so stable that it's okay to do it sequentially because you don't get errors between gates. And so, you know, normally there's this theorem which says that if you want to do fault tolerant computation, you have to do parallel, you have to apply your gates in parallel. Otherwise your errors are just going to decimate the computation. Whereas here one sort of says, well, the gates are happening, you know, the ions are so stable that it's okay, you can do one gate at a time. So this would seem to imply that you only need to worry about the one gate. So in the other, you know, in your other scenario you mentioned, would it still apply that you're, you know, that you could rely on your single gate errors to say, well, you know, it's okay to do the gate sequentially?
Sorry, the question is whether the sequential gate is subject to the kind of single ion errors versus.
Yeah. So my, you know, my picture of ion trap quantum computing is that you do one gate at a time, but you mentally, our model is that the rest of the ions are perfect, so they're never subject. You know, while we are waiting for that one gate to apply, nothing else is happening. So you know, so if we take all this into account, does it still work out? And
I think that's an okay assumption for the ion trap quantum computer, honestly. The actual qubits themselves sitting in the dark are very, very good compared to the other timescales involved. Yeah. Now that doesn't mean that you know, you shouldn't start doing things in parallel. There are lots of things that can be done in parallel, including 2 qubit gates if you do it right. But you know, I think your assessment is probably reasonable, which is that most of us don't worry about it because the qubits are just so darn good that you know, we're not pushing that particular. That's kind of a, you know, that's a second order lever that we're not really grabbing onto yet, I would claim.
So maybe it's a good time for this question. So in light of the beginning of your talk, Wes, where you mentioned the Google result and Umesh's question about the difference between what's going on at IonQ and the work that you presented. Where's this question? How do we take the leap from proof of principle quantum supremacy tests to a system that allows us to answer new questions? And this doesn't just have to be a question for us. This is sort of for everybody. So we can get into the discussion.
Yeah, that's the question.
The big question.
We're going to be asking this every week. Yeah, I mean, I tried to advocate for errors. Errors are the problem, not scaling. You know, let's beat on the errors, and instead of building something with 10 to the 8 qubits in it that don't work really well, it seems like we have some advances to do on just lowering the overhead required to deal with the errors that we have. But that's not the only opinion that's reasonable, I think.
Maybe along those lines, Wes, I mean, actually something that I just don't know. I mean, so you emphasize like a lot of these different kind of atomic properties that are super important for control at the level of like single ions. do any of these differences in just, picking the element, do you see any of that impacting scalability, or is that really not, or is the scalability challenge kind of more or less uniform across different ions?
Yes, that's a good question. I mean, I would claim that ytterbium is too heavy to be wonderful for using motion. So the kind of the quantized harmonic oscillator levels that Charles showed you, the splitting of those depends upon the mass, the charge to mass ratio as well. And ytterbium, I would much rather work with something whose structure was just like ytterbium, except had a mass of like, an alpha particle instead of 171 nucleons. And so that is an aspect of it, but it's not the same as neutrals, right? I mean, with neutral atoms, you've got scattering properties are totally different for just two different isotopes. I mean, it's really a different level of the knob that you turn when you change the internal structure also changes the interactions in a really fundamental way. With ions, it's kind of, well, the mass, right? That's sort of the only kind of extrinsic property that changes there.
Maybe just following up on Charles's question, really just one more question. So, there are experiments in trapped ions that operate kind of either analog, as you addressing to motional modes, but also ones that operate digitally. Just from your perspective, in terms of taking the first step beyond supremacy type experiments to, things that are, less like, a little bit more useful, do you feel like that's going to come in the digital operation domain or in the analog operation domain?
That's a good question. I think it's, verification in the analog domain is really tricky. And that's, something that I know that, I think you've thought about. Hartmut certainly, has thought about, that is, I think, the challenge may not be performing an experiment that can't be done quicker by a classical simulation, but the challenge there is probably demonstrating that it did the thing you wanted it to do. And so that would be the missing link there, I guess I would say. And there are people who have some ideas on that that are good, but probably more work there would be needed for the analog thing to win, because the digital simulator, I think it's a little bit easier to say, well, we can verify that, we can calibrate the gate fidelity and verify it, and maybe even use some error correction or something, like whatever it is. Just my opinion, I don't know. Maybe you can write a big RMP review article on it and tell us.
I have a question about scaling, which Umesh was getting at, and I wonder: is there good quantitative work that shows what gets worse with system size and how that scales? And you gave a few explanations for why that could happen. Let's say photon absorption by neighboring ions. So there, I feel like I can write down a geometric factor and look for it. Look for evidence of it in my experiments. Is there good work in this area, or is it just, oh, I don't know, things get complicated, so things get worse?
Yeah, I think it's the latter. I'm not aware of anybody who has really approached the modeling of the scaling problem on a kind of a fundamental level. So I think that's, there's room there for that, for sure.
Yeah, maybe, I don't know if I should jump in, but the QCCD architecture is trying to solve this problem. When you basically, the idea is to show all primitives, and that scaling should just work. But of course, yeah, I mean, the devil is in the details, so we don't know. The other thing is, like, if you wanted to stick to a single crystal, The way the gates are enacted is by a single photon scattering off this crystal and actually imparting motion onto the whole ion crystal. So if you're having longer ion chains, you're increasing the mass of your ion crystal. And this is how actually the gates get slower with the square root of the mass. And that is, for instance, I think would be a good approximation. Maybe you can make how actually the quantum gates will deteriorate with longer ion crystals. I'm not sure of a systematic study who verified this actually, but this is what I always assumed.
Yeah, it could be maybe just to amplify a little bit on what Hartmut said. You know, as you put more and more ions in a single crystal, the thing that can happen is the modes get denser. The motional modes get more dense, at least in the transverse modes. It depends which modes you're using, but for the transverse ones, they get more dense. And so if you want to hit one and not hit the other ones, that's the origin of the reason it gets slower, I guess that Hartmut was saying. For the longitudinal modes, you do have modes that start to really get quite low in frequency due to the mass scaling. So there's two different effects happening there.
Eric, can I bring you back to your provocative but also very weird slide about what you'd want other people to work on? Are there any of those ideas that you want to share?
What was black holmium?
Black holmium, yeah. So black holmium is like if you have a Planck mass scale black hole, maybe it's dark matter, okay, I don't know. It can be charged. I don't know if you guys have ever heard about this. Has anybody ever heard about this? So, and the charge it can have means that it can have an electron on it, and it can be an atom. And so the idea there is that, you know, it's probably not that hard for someone to kind of go through this and figure out what limit you could put on this based on astronomical observations. You can calculate the spectrum of it, right? I mean, it's kind of like an isotope where the mass has gone to infinity, right? Of the nucleus, it's gone to infinity. But then you could do chemistry with it in principle, and that could be happening. And so I don't think anybody has thought about what happens if one of those becomes a molecule. If it's a black hole with some electrons on it and then an atom, it's going to have rotational transitions and vibrational transitions where one of the masses is effectively infinite. And that spectroscopically should show up. I don't know. Look, I don't know anything about black holes. Nothing. Okay. There's almost somebody else to do this. Okay. And apparently also it can, in principle, you know, I don't know, but, you know, according to the paper by Flambaum and friends, capture a single quark, which means that if you had an ion trap and you were trapping black holmium, you could trap a quark. So that's what you get for asking about it, Dan. That's black holmium. But somebody should, I don't know, like somebody should do this. Not me, but you know.
Awesome. What a way to finish up this section. So it's actually 1:40 now. Very exciting way to finish. That does mark the end of our focus discussion. So now, for the remaining 20 minutes, the faculty would leave the call, and we'd have 20 minutes or so, the grad students and postdocs, to have a conversation with Wes. So thanks everybody for coming. Faculty, please go about your day.
Thanks everyone.